Okay, so let c be the part of y squared plus c squared equals 16 in the first octant between x equals 0 and x equals 9. Here's a function. We want to compute the surface integral of a scalar valued function. Okay, this is different than the surface integral of a vector field. Okay, so the surface integral of a scalar valued function, for these, orientation does not matter. We're going to do later surface integrals of vector fields, and then orientation of the surface does matter. But for this, it doesn't matter. So for example, f might be like the mass density of the surface, and this integral would then represent the mass of the surface. Okay, but f can be whatever you want it to be. Okay, so first of all, y squared plus z squared equals 16. This is a cylinder of radius 4 centered in the x-axis, centered on the x-axis. The first octant just means we just want the part in the first octant, and we just want the part from x equals 0 to x equals 9. So the projection of this shape onto the yz plane is going to be like this. This is why this is the projection of the whole cylinder is going to be the circle of radius 4. Okay, but we just want the part that's in the first octant. Okay, so that's going to be the first quadrant in the YZ plane. Okay, and then this is going to like come out of the screen to x equals 0 to x equals 9. Okay, the axis coming out of the screen is the x-axis. So the formula for a surface integral, let me get rid of this for now. The formula for a surface integral is this. This is the surface integral, or the integral over parameter domain D. The parameter domain D is in a plane. It's in the plane. F of R of ST times the magnitude of RS cross RT ds dt. This integral D is in the ST plane. Okay, and R of ST is a parameterization for the surface, and S and T are the parameters. Okay, so the parameterization for this surface, well, the parameterization just for the whole cylinder is going to be R of theta T, R of theta R. Let me be consistent here. R of theta R is equal to R for cosine theta for sine theta. Okay, so in a previous video, I got the parameterization for a cylinder in the z-axis. This is a cylinder on the x-axis. So now y is going to have the cosine theta and z is going to have the sine theta. Okay, and we saw before that, so we need to figure out what the parameter domain is. So we know that r is going to go from 0 to 9, and we know that theta is going to go from pi over 2. Okay, and again, theta goes between pi over 2 because the projection of this shape into the YZ plane is just going to be this quarter circle right here. It's this quarter circle of radius 4. And we only want the quarter circle because it's the part of the cylinder that's in the first octant. Okay, so now when you're doing these integrals, whether it's a surface integral of a scalar valued function, or if it's the line or the surface integral of a vector valued function, just take your time and fill in each one of these pieces. Okay, so we already figured out what R is. Now we need to figure out what this cross product is. So R theta is equal to 0 minus 4 sine theta for cosine theta. RR is equal to 1, 0, 0. And I will let you guys check this. But the magnitude of R theta cross RR is equal to 4. Okay, so now let's just start filling stuff into this integral. Okay, so obviously there's S and T here, but our parameters are theta and R. So the domain is going to be R equals 0 to 9, theta equals 0 to pi over 2. Okay, now I need to fill in the function. So what is f? Well, here's my formula for f. Here's my formula for r. So wherever I see a z, I'm going to put 4 sine theta. Wherever I see an x, I'm going to put r. Wherever I see a y, I'm going to put 4 cosine theta. So this is 4 sine theta, that's z, plus x squared. X is equal to r. So this is going to be r squared times y. Y is 4 cosine theta. So this is 4 cosine theta. Now I'm going to put this, the r theta cross rr, that's this part. This is 4 dr d theta. Now this is sort of like a polar integral coordinate, all right? Or I'm sorry, polar coordinate integral, but we did not start, at least the way we're doing it, we did not start from a Cartesian coordinate integral and end up in a polar coordinate integral. So do not add an extra r right here. Do not put an r here because we're not going from Cartesian coordinates to polar coordinates. We're starting with this integral here that kind of looks like polar coordinates, and because it really is polar coordinates, but we're not going from Cartesian coordinates to polar coordinates, so do not put an r there. Okay, and so you can compute this integral, and this is equal to 4,032. Okay. Obviously, I'd already done that, but this is an easy integral to do. Okay. All right. So again, this is the surface integral. The big thing to remember is this is the formula. Okay. So the new part in this problem is just getting down to this piece. And now you can do this integral whatever way you want, whatever mathematically valid way you want to get to 4,032. So just remember this formula. This is the surface integral for a scalar field or a scalar valued function over a surface. It's different from a vector field over a surface. Just remember this formula right here. And as you're doing these problems, just very carefully identify each piece and write down each piece very carefully. Don't try to skip ahead too much until you get to be very comfortable with it.